All right, it's a small crowd, but nonetheless a very distinguished crowd. So welcome everybody to our seminar of today. Welcome all you here in the ether. Today we have Evan Kalina from NOAA here to give us a talk. Before he starts, let me give you a little introduction. He is a National Research Council postdoc at the moment at NOAA, AOML and Aerosol, located here in Boulder. Lucky you. Mm-hmm. Congratulations. A little background on his research. His research interests include using numerical models and radar observations to understand precipitation processes in severe thunderstorms and tropical cyclones. He's played a vital role in a few field campaigns, Vortex 2, verification of the origins of rotation in tornadoes experiment. We deployed disdrometers and surface observation stations in supercell thunderstorms. And he's been with the Hurricane Research Division annual hurricane field program. And he just told me he's been on 6 hurricane flights so far, flying on the P3, and they're also working with the Coyote unmanned aircraft system that's being deployed from those P3s. He also collaborates with a bunch of folks here at NCAR, and I guess most of you know him for that reason, as well as at CU and the National Weather Service Forecast Office in Boulder, to detect and forecast accumulating hailstorms along the Colorado Front Range. He got a bachelor at Florida State in 2010, and last year his PhD here from CU, working with Katja Friedrich. And I was actually quite surprised. I looked up your publication record. So it's 7 publications so far, including 3 as a first author. That's quite well done. Keep going on this one.
Thank you.
That's good. All right, today's talk is about investigation of severe microphysics and investigation of severe storms microphysics using models and dual-polarization radars. Evan, please.
Thank you, Holger. Oh, yes. All right, so thank you for coming, guys. So today, as Holger mentioned, I've done a few different research projects in the area of severe storm microphysics, and I thought that I would present on 2 of those topics to you here today. So the first study that I'll show you results from is a modeling study. It looks at aerosol effects in supercell thunderstorms using the WRF model. And there's been a number of different research groups that have looked at this problem in the past. But the goal of this study was really to look at the entire range of cloud condensation nuclei concentrations in the atmosphere that are possible. So instead of just comparing a clean simulation to a polluted simulation, we really want to see how the microphysics and the thermodynamics of these storms are affected across that entire spectrum of pollution concentrations. And not only do we want to look across the CCN spectrum, but also looking at different environmental conditions that are conducive to supercell thunderstorm formation. Obviously, the supercells we get here in Colorado often form in a much drier environment compared to the ones that form in the southeast U.S., and we want to see how these aerosol effects vary if you change the relative humidity or change the wind shear of the environment. So that is the first part of the talk today. And the second part of the talk will transition to an observational study and take a look at how dual polarization radar can be used to do some ice water path retrievals from recent landfalling tropical cyclones in North Carolina. The purpose here is to understand the types and amounts of ice that we have in tropical cyclones. It's traditionally difficult to observe above the melting layer with aircraft in these storms, so we are trying to use the dual polarization radar to understand this question. And principally, we want to know how much water path is contributed by ice crystals compared to some of the larger particles that have a non-negligible fall speed like graupel or snow, because getting this ratio right is something that numerical models have had a lot of trouble with in the past. And we need some observations to do validation studies with the models. So on that note, I'll begin with the first part of the talk, looking at aerosol effects in supercell storms. So this comparison here between a couple of different studies, one done in the late 1970s and one done just a few years ago, is really amazing to me. To see the advances that have occurred in computing power and model microphysics sophistication over these past few decades. On the one hand, you can see that this early study had a grid resolution of 1.5 kilometers, which I imagine at the time was rather state of the science. And the microphysics scheme was quite simple. The Kessler scheme doesn't even include ice processes. It just has a couple of liquid microphysical species within the storm. And it also assumed that the number concentration within the microphysics scheme was set constant, and that we know, of course, now that that's not really a reasonable assumption in the real atmosphere. Contrast that study and its assumptions to something more recent, where we have more than an order of magnitude improvement in the grid resolution of the model. We have a much more complicated microphysics scheme that includes not only rain, but also several ice species in the model. And it predicts both the number concentration and the mixing ratio of each species. And you can see all of this fine-scale structure within the supercell storm that we maybe even couldn't imagine simulating a few decades ago. So there's then this vast increase in complexity of these schemes and also computing power. And of course, we were wondering, how can we best use these resources that we have within the community? And should we, for instance, devote resources to modeling supercell thunderstorms and the aerosol effects within them? You might imagine that if aerosols can really perturb the supercell storm enough that you get different outcomes, whether that be in regards to tornadogenesis or the amount of accumulated precipitation, you might imagine that we need to assimilate some of these aerosol concentration measurements, maybe even create an observational network to collect these types of observations. Of course, if it's not important, we don't need to devote resources to that. But there's no question that, at least from the environment, these storms are entraining aerosols into them. This is an example from the High Park fire in 2012 in Colorado, where we had a supercell thunderstorm develop downwind of the fire location. And you can see from the satellite and the radar imagery that the storm is clearly in proximity to these smoke plumes from the fire. And this is a picture taken from the deep convective clouds and chemistry experiment from one of the aircraft. And you can see that the smoke is becoming entrained within the storm itself. And the question is, how does this affect the supercell? And are the effects important enough that we really need to consider these in our simulations? So I'd like to provide a bit of background on what we know so far about aerosol effects in thunderstorms. For one, when you add pollutants to the atmosphere, you increase the number of cloud droplets that you have in the storm. And because there's a limited amount of liquid water, as you might expect, the sizes of these cloud droplets tend to be smaller, since you've distributed the liquid water across many more particles now. However, something that might be a bit less intuitive is that the raindrops become larger because they can now collect all of these tiny cloud droplets that they encounter within the storm. And because these raindrops are larger and have a greater sedimentation velocity and can reach the ground more quickly, the cold pools tend to be weaker as there's less evaporation from these larger precipitation particles. However, there are some remaining questions that previous studies have not analyzed in much detail. One being, what is the effect on hail particles? Can we draw this same analogy that we do for rain to hail particles as well? And in addition to that, how is the accumulated precipitation from the storm affected? There's been a number of conflicting results within the literature. Some studies have shown that the accumulated precipitation should increase as we increase CCN. Others have suggested that it should decrease. So what is the reason that we have these discrepancies in these studies? And finally, what is the dependence on the relative humidity and the wind shear? Because supercell thunderstorms don't just form in one exact environment with the exact relative humidity or wind shear value. There's really a range that supercell storms form in. So how do all these relationships, how are they affected by the environmental conditions? So the method here is that we will use the weather research and forecasting model for doing this research. These are highly idealized simulations in that they don't have a boundary layer or surface scheme. They don't have radiation schemes in the simulations. And the reason for doing that is really to isolate the effect that aerosols have on the microphysics. So we don't really want all these second-order feedbacks that can be triggered by radiation when we change the amount of CCN concentration. We really want to understand what is the direct effect within the system that we're modeling. So the storms within the model are initiated with a warm bubble. The sounding used has a large amount of potential instability that can then be ignited with this warm bubble. And the simulations are relatively high resolution, 1 kilometer in the horizontal and 300 meters in the vertical. And as I mentioned before, we're going to explore a range of CCN concentration, anywhere from 100 per cc to 10,000 per cc. And this, we believe, really represents the range of aerosols that these storms might encounter. And finally, we'll use 4 different environmental soundings for these simulations to explore the effect of environmental conditions on the results. A little bit about the microphysics scheme. It's the Morrison double moment scheme, considering these 5 species of rain and ice within the storm. And each of these species are parameterized through a gamma distribution, shown here. And the CCN spectra is basically a simple power law, whereas the supersaturation within the cloud increases, the number of CCN that are activated increases and can then serve as cloud droplets within the storm. And the chemical properties of these CCN are those of ammonium sulfate within the model. So here are the 4 different soundings that we consider. You'll notice that all the soundings are the same, with the exception of within the lower portion of the atmosphere, there's variation within the amount of relative humidity from the different soundings. So we have a low relative humidity simulation with approximately 61% RH. We have the default sounding with something that's in the middle of the low RH and the high relative humidity cases. And then we have this high RH case that has 91% relative humidity. We also do some manipulation of the vertical profile of the wind in these simulations. So we have the default sounding with a bulk shear of about 8 meters per second, and then we have a high wind shear case, or high WS, where we double the amount of wind shear in the simulation. So 4 different sets of simulations, if you will. Here's an example of a storm from one of the simulations from the default sounding. You can see that about 30 minutes of integration time, we get our first indication that a supercell is beginning to form. And as we continue to integrate forward in time, we get some of those many expected supercell features, like a hook echo developing and splitting cells within the storm. And as we progress further into the simulation, you can see that these storms continue to develop and become larger and begin to move away from each other with a left mover and a right mover. And at the end of the simulation, which is at 2 hours forward into the future where we cut it off, you can even see some of this secondary convective development that you would typically get in nature. And that's where we stop the run so that we don't start analyzing the aerosol impacts in these smaller secondary cells that are beginning to form. So now I'm going to show you a number of these domain-averaged vertical profiles where we have height on the y-axis and quantity of interest on the x-axis on the bottom. So in this case, we're looking at the mean mass diameter of 3 different species of hydrometeors, cloud droplets, rain, and hail in the different colors. And the different lines that you see here, the dashed line is the most polluted run, the 10,000 per cc. And the solid line is the cleanest run that we looked at, 100 per cc. And so if you look at how the mean mass diameter changes as you add aerosols, one thing that we see, which we already expect, is that these cloud droplets become about 3 times smaller as we move to polluted conditions. And that's something that other studies have seen. It gives us confidence in the results that we have here. And if we look at the rain and the hail particles, we also see that there's an increase in their diameter as well, by about 30% within the low levels for rain and approximately 3% for hail. And so you can see that what we expect is that we have larger raindrops, and indeed we do. However, we can already see that analogy for the hail particles mostly holds up when we look at the simulation, although the effect on the hail is a bit less than what we see for rain. So these profiles look remarkably similar if you were to explore the high RH case compared to the default case, or the high wind shear case compared to these. So I'm not going to show you all the profiles from those since the results are basically the same. However, the low relative humidity case as well, although there are higher cloud bases obviously within that simulation, the results also look pretty similar. So we're not seeing a lot of gradation based on the environmental conditions yet if we're just looking at the mean mass diameter of the particles. So now let's take a look at the profiles for the mass mixing ratio of the different hydrometeors. Again, when we look at the cloud droplets, we see something expected. As we go from clean to polluted conditions, we increase the amount of cloud droplet mass, and we leave more of the water vapor or water within the cloud droplet species compared to the rain and the hail. However, I'll point out within the low levels where there is a bit of a discrepancy to that argument. You'll see that with the hail mass mixing ratio profiles, we actually end up with more hail mass within the low levels in the polluted case, which is somewhat contrary to what we see with the rain and perhaps contrary to what we'd expect. And that's really due to larger hail number concentrations within the low levels. More of these hail particles have survived below the melting layer because of their larger size, and we end up with more hail mass in the lower part of the atmosphere. So these results look very similar for the high relative humidity sounding. There's really only a difference of 11% in relative humidity between the default and the high RH run, so we wouldn't really expect that big of a difference. But if we look at the low relative humidity case, the results are quite different within the low levels. You can see that regardless of whether we look at a clean or a polluted simulation, the hail masses are basically constant within that part of or not constant, but very similar within that part of the atmosphere between the two types of runs. In this case, the low RH case is similar to the high wind shear case. So if we summarize here, the default and high RH cases have more hail mass in the low levels when we go from clean to polluted conditions, whereas within the low RH and the high wind shear cases, we don't really see much change in the amount of hail mass between clean and polluted conditions. And that has important effects on the thermodynamics of the supercell storm between these two sets of simulations. So I'll elaborate now a bit on that. What I have here is the rain budget. This essentially shows you the microphysical process rates within the supercell storm. And I've plotted the change in rain mixing ratio on the x-axis. So processes like evaporation that lead to a reduction in the rain mixing ratio are represented as a negative quantity, whereas processes like cloud water collection that contribute to rain-water mixing ratio are represented as positive quantity. So I'm going to focus on looking at how the evaporation rate is affected by aerosols within these supercell storms. So as we go from clean, we're represented by the solid curve, to polluted conditions, there's a reduction in rain evaporation that's expected based on the larger raindrops that we have within the model. What do we see for hail? If we look at the hail budget, where melting is essentially the analogous quantity to evaporation of liquid particles, we actually see completely the opposite situation occurring. As we go from clean to polluted, we end up with more melting and more cooling. And that is, again, a result of having those larger hail masses within the polluted conditions within the high RH simulation. So we essentially have compensating trends here within the low levels, where we have reduction in the amount of cooling from evaporation, but more cooling from melting within the higher H run. That has profound effects on the cold pool, that amount of rain and hail-cooled air that's located within the low levels of the storm. So because we have those compensating trends between the rain and the hail, we really don't see much effect on the cold pool as we increase the CCN concentration from clean to polluted conditions. You can see that the area here of the cold pool is essentially constant, and really doesn't care how many aerosols there are within the model. And the temperature, which is represented by this dashed line, the mean temperature of the cold pool, really doesn't change very much either. It changes by a few tenths of a Kelvin. It's not really a very important change. And you can see that the results are very similar from that higher H sounding. And remember, we've grouped the default and higher H cases together within our results. So now let's take a look at the ones where we don't see these compensating trends within the low levels. You can see that for low RH, we have this reduction in evaporation as pollution increases. That's what we expect. And when we look at the hail budget, we also see a reduction in the amount of melting and cooling within the boundary layer as well. So rather than have compensating effects like we did in the higher H case, these two effects both are moving in the same direction to reduce the amount of cooling. And when we look at the cold pool properties from this run, you can see that as CCN concentration increases, you get this marked reduction in the area of the cold pool, and the cold pool warms much more notably than in the high RH case. So, and you'll also notice from this plot that a lot of the effect actually occurs within the first couple thousand per cc increase of CCN concentration. And that's important because it tells us that we really don't need to add a tremendous number of aerosols to the atmosphere to get some of these microphysical and thermodynamic effects. You can actually have them at relatively pedestrian CCN concentrations. And this is just to show you that you see a very similar result with the high wind shear case as well. In terms of the cold pool properties. So I mentioned that we'd also take a look at the effect on accumulated precipitation within the runs. And there's basically two different sets of simulations here as well. If we look at the high relative humidity sounding, you'll notice that there's all of these warm colors along the approximate path of the updraft tracks, which are shown in the closed contours here. And that indicates that there's been an increase in precipitation in those locations as we increase the aerosol concentration. So aerosols are leading to more precipitation being output along the updraft tracks within the high relative humidity case. If we reduce the relative humidity and do the simulations, we see exactly the opposite has taken place, in which we have a reduction of precipitation nearly across the entire domain as we increase the CCN concentration. That's really an effect of having a non-optimal balance between the amount of available water and the number of CCN that we have within the storm. You've simply overloaded the system with so many pollutants that you're no longer getting enough precipitation-sized particles out of the storm. And so this is really, certainly be an explanation for why we often see conflicting results on how pollutants influence the accumulated precipitation, because it depends on the environmental conditions that have been used to initialize the simulations. So to wrap this portion of the talk up, I've sort of made some of these slider bars to summarize the results. And so compared to clean conditions, polluted environments lead to less cooling from evaporation, regardless of what environmental conditions you use to initialize the simulations. However, if you look at the cooling induced from melting hail, whether you get more cooling or less cooling as you increase the CCN concentration really depends on your initial conditions. If you have relatively high humidities and moderate values of wind shear, you end up with compensating more cooling from the melting hail, and that compensates from this reduction in cooling from the evaporation. So when we look at the cold pool properties, you can either end up with relatively no change from those compensating sources of cooling, or you can really play a large role in changing the properties of the cold pool in a low relative humidity or high wind shear case, where the cold pool will shrink or warm in response to these different sources of cooling. And if we look at the precipitation, there's generally a modest increase in precipitation in all the simulations that we looked at, except for the low relative humidity case, where there was a dramatic decrease in precipitation as the aerosol concentration was increased. So I think we, before moving on, we have some time for a few questions, if you guys have any.
So when you talk about the clean conditions and the polluted conditions, how did you introduce those additional CCNs or pollution? Was it just uniformly over the whole domain, or was it in the lowest layer? How is that, distributed, and is that even a factor or make a difference in how the storm ingests it and processes it and spits it back out?
So certainly within the real atmosphere, the vertical profile of CCN would play a role in how the storm interacts with the CCN and ultimately how much change you get in the microphysical or thermodynamic properties. In these simulations, though, it's a very idealized setup. So there's actually a constant profile of CCN concentration with height. So we're not really accounting for the fact that in the real atmosphere, we would probably see a lot more CCN in the boundary layer as the storm kicks up dust and other pollutants off the surface. And another relatively simplifying assumption about the CCN scheme is that your number of CCN and cloud droplets are held constant within the microphysics scheme. So you can convert from CCN to cloud droplets, but then as soon as you convert a cloud droplet to a raindrop, you then add that CCN back into the system. So you're not exactly getting scavenging of the CCN out of the cloud within these simulations. So those are a few important things to keep in mind, and reasons for why maybe the exact magnitude of the responses might be different in the real atmosphere.
And the smoke case, too, is more complicated because then the storm is doing something with a point source.
Mm-hmm. And what level was it in training? And
to imagine it being just sort of uniformly distributed throughout the storm.
Definitely.
So I think the bottom of this slide probably answers my question, but on the previous slide, I was just curious in the high relative humidity case, what is the effect on the overall precipitation? Because there's the zone of diminished precipitation and zones of increased precipitation.
Yes. So if you look at the domain averaged effect, it is an increase in precipitation. The increases are larger in magnitude than the areas where there's those decreases.
Okay.
All right. I
Question?
will proceed forward. So the second part of the talk is some more recent work that I've been doing with colleagues at the Hurricane Research Division and also at the Physical Sciences Division and right here at NCAR. We're looking at using dual-polarization radar to understand the ice water paths within the tropical cyclone, and specifically how these ice water paths can be partitioned between different ice species within the storms. So I'd first like to spend some time showing you that it's plausible that dual polarization radar can be used to do this, since this is a relatively new research area. And I'd also like to show you what the ratio is between the ice crystal water path, or these relatively small ice particles that are suspended within the storm, versus the ice water path from these precipitation-sized ice particles like snow and graupel. And that ratio is important from getting the radiative balance correct within the tropical cyclone in numerical model simulations. And finally, I'll consider whether this ratio that I'm talking about should vary between stratiform and convective conditions, or whether it really doesn't make a difference whether you have stratiform or convective precipitation. So to give you some background, this is the typical cross-section through a hurricane that everyone is familiar with, and overlaid is some simple microphysical information included there. So you'll notice that within the updrafts, we have these snow and graupel particles within the storm. Those are what we're referring to here in this study as large ice, and what some people may refer to as precipitating ice. And you can see that the areas where these particles are concentrated tend to be in the rain bands, or especially within the updrafts within the eye wall. Now, there is some graupel contained within a hurricane, but it's a relatively small amount. Most hurricane updrafts, except for the most intense, are glaciated above about -5 degrees C. And so we really don't have a lot of liquid water to work with above that level. But nevertheless, in the strongest ones, you may see some graupel, but predominantly it's snow and aggregates of snow particles. Above those larger ice species, we have the small ice, or the ice crystals, suspended within the anvil of the tropical cyclone. And these particles play a very important role in the radiative balance of the storm. For instance, the size and the fall speeds of these ice crystals really determine how much of an anomaly that you get within the vertical above and below the anvil of the storm. We know that there's subsidence below the anvil of the storm due to sinking air, whereas there's cloud top radiative cooling above it. And the amount of that cooling and warming, respectively, is often controlled by these ice crystal sizes, or at least partially attributable to the ice crystal sizes within the storm. And the reason that that is important is because if you change this vertical temperature profile, you can exert changes to the horizontal pressure gradient within the storm. And through that, you can directly influence the intensity of the tropical cyclone. So this is one of the reasons why microphysics plays an important role in the forecasting of these storms. So that was a schematic, but these are some results from actual modeling simulations that different people have looked at. And I'll point out here that the Kessler scheme, which we discussed earlier, is relatively simplistic. It doesn't even have any ice within the storm. So we might be skeptical of the results from that scheme. And I should back up and say that what we have here is the total condensate in the precipitation fields shown here, and these are essentially the same vertical cross-sections that I showed you earlier. But even if we go to a more sophisticated scheme than Kessler and look at LFO or WSM3, we still see pretty dramatic differences in this depiction of the amount of total condensate within the anvil of the tropical cyclone. And the x-axis here, I'll note, is in degrees of longitude. So a relatively small-looking difference here in the extent of the temperature perturbation or the extent of the total condensate field is actually really quite large in reality. So we know that we can get these different depictions of the anvil and its properties depending on the microphysics scheme that we choose in our simulations. But the question is, which scheme is correct? We might be tempted to say that LFO, which has the most hydrometeor classes in it, because it's the most complex, might get the best depiction. But without observations, we really cannot say for sure or perform any validation. So how can we use radar to get at some of these observations of ice fall speeds and ice water paths to validate our models with? Well, taking a look at the vast improvement in the technology of the 88D network within the last few years, it can give us an answer to this. So as I'm sure many of you know, dual-polarization radar transmits both horizontally and vertically polarized radiation. And as a result, it causes the radar to be sensitive to all different kinds of microphysical properties, like the particle shape. And we can use algorithms that look at the particle shape and the particle orientation to give us the types of ice or the types of species that might be present within the storm. And we can also do things like take integrated quantities like the ice-water path or use it to detect the melting layer height. So for people who are interested in storm microphysics, this is really an excellent tool that we now have at our disposal. And there's upwards of over 100 radars within the country that have been upgraded to this capability, and many of them lie within hurricane-prone regions along the coast, like the radar in Morehead City that we'll be using in this analysis. About the only thing that we would like microphysically to get from the radar that we really can't get with the scanning dual-polarized radar is some estimate of the fall speed of the precipitation particles within the environment. And we are lucky in the sense that the scanning radar in Morehead City was for a few years coupled with a vertically pointing radar deployed by NOAA Boulder. And so we can match the beams projected by the scanning radar and the vertically pointing radar and use this to couple the scanning radar's hydrometeor classification with the fall speed measurements made by the vertically pointing radar. So now we just needed a few storms to go past this configuration to be able to collect some data. And the atmosphere delivered with Irene in 2011 and Arthur in 2014. Two Category 1 storms that both made landfall very near the radar in Morehead City, only about 30 kilometers away. And you can see that Arthur was a very relatively symmetric storm, whereas Irene was somewhat more sheared from the southwest. But we have two potentially good cases here to analyze data from. And I will start by showing you some of the reflectivity and the fall speed measurements made by the vertically pointing radar in Hurricane Arthur. And again, these are essentially stratified by the hydrometeor classification from the scanning radar. So when we do this, we can see that the results initially make good sense, where we have increasing reflectivity as we go from ice crystals to dry snow to more heavily rimed particles like graupel within the storm. And we also see that as we go to some of these larger particles and more heavily rimed particles, we also see increase in the amount of fall speed that's detected by the vertically pointing radar. So this might seem trivial, but it's actually quite important that we're getting some of these separations between the different ice species, because it tells us that the scanning radar's particle identification scheme is working and performing relatively reasonably. I'll also note that there's this very sharp drop-off in the fall speed distribution for the ice crystals that are detected by the radar. Right at about a quarter meter per second, we really don't get much more ice crystals detected by the radar. Now, that's not to say that there aren't more ice crystals there that have those smaller fall speeds, but this is essentially a detection limit that you're seeing. The scanning radar is S-band, and so is the vertically pointing radar. And so with such a large wavelength of radiation, we're really not sensitive to ice crystals that have a very negligible fall speed. And that's something that we're going to keep in mind when we look at the results later on, detecting the amount of ice-water path within the storms. So with that caveat in mind, we can use these distributions to compare to the output of some of our model microphysics schemes, keeping in mind that we have to restrict the fall speed to about a quarter of a meter per second or more. And we can use them to diagnose how reasonable is the microphysics scheme. I'll also note that there's this area in the data where there's considerable overlap in the fall speeds between ice crystals and dry snow. And this is a region of the distribution that might give us some pause, and we may ask, can the radar really differentiate between large ice crystals and relatively small snowflakes? Or is there some ambiguity there in the dual polarization variables? And so we wanted to take a closer look at these relationships between the fall speed and the reflectivity of different ice particles, notably the ice crystals and the dry snow. So what you see here is a two-dimensional histogram with the intensity basically contoured in these lines. And the ice crystal distribution lines are shown in solid, whereas the dashed lines indicate the properties of the dry snow distribution. And when we look at this diagram, what we're looking for is that, okay, first of all, we have quite a bit of separation in the phase space between ice crystals and dry snow. So it's plausible that the radar is seeing some different particles within the atmosphere between these two phase spaces. You'll also note, however, that there is that region of overlap that we talked about before within the fall speeds. However, in a mean sense, this actually is very encouraging, because if you do regression relationships between the fall speed and the reflectivity for ice crystals versus dry snow, you can see that there's actually a very different relationship between the two. And that difference in the relationship suggests that in a mean sense, not necessarily on one radar volume, for instance, but in a mean sense that the radar is actually detecting two microphysically distinct particle types within the storm. At least that is the way that I would interpret this result. So being that we can, in a mean sense, diagnose the contribution from ice crystals versus other ice species, how do we use the radar to estimate what the ice-water path is between the different ice species? So this is a method that was developed by Sergei Matrosov over at NOAA Boulder. And we're just going to explore it on a very idealized volume scan with only 3 elevation angles. Obviously, there would be more, but this is just an idealized look. And so we can estimate the ice-water content within each of these radar beams using this relationship between the reflectivity and a temperature profile provided by a radiosonde that was launched in the hurricane environment. And we can use that to get this ice-water content estimate. This is a relationship that was derived from about 10,000 particle-size spectra collected by aircraft within the United Kingdom. And it's was collected over a temperature range from about -3 degrees C to about -57. So we're really able to get a pretty good look at both some of the larger ice particles that might be within the lower, warmer part of the atmosphere and some of those colder ice crystals that are within the higher portion of the storm. And so we can integrate the ice-water content within these set of radar beams to give us our ice-water path. And that's shown by the contribution here. But we have to do a little bit, be careful with our mathematics and make sure we don't double count areas where the beams overlap, and that we also take care to interpolate between beams where there's gaps within the vertical. And so if we do all this, we can get an estimate of the ice-water path within the storm. Finally, we're going to go a bit further than the Matrosov paper did, and we're going to separate that into the different types of ice within the storm and also look at how those, the ratio between the ice crystal water path and the snow water path varies between stratiform and convective conditions using the Steiner and co-authors' separation algorithm. So here's an example of a radar scan looking at the radar reflectivity. You can see the rain bands and the center of the storm here off to the lower left with a considerable amount of convection in the eye wall and also this outer region. And using the method that I showed you, we can essentially map out the total ice-water path field within the storm using that method from the radar. You'll notice that there's this area of missing data here that I've whited out. That's because that's where we're so close to the radar site that the radar volume has not yet extended up to the top of the atmosphere, which we're calling here about 15 kilometers. So looking at the ice-water path here would not be a total estimate. But beyond that, we can get a decent idea of what the ice-water path field looks like. And we can see that there's some distinctions within the field or general patterns that occur. Within the intense rain band convection and also within the eye wall, we see some of our largest values of the total ice-water path, upwards of 10 kilograms per square meter. And we can also see within these contoured regions, that is the area where the Steiner and co-author scheme identifies active convection within the storm. So we can see that a lot of our largest ice-water paths are contained within those convective elements, but they're certainly not completely confined. We also see in the more stratiform regions, there are areas of considerable ice-water path within the storm as well. We can then partition that, as I've been promising you, and get essentially a map of where the ice crystal ice-water path is in the storm and where the snow ice-water path is within the storm. And this also includes contributions from Grapple, but since there's relatively little Grapple within the storm, this is essentially a map of the snow within the storm. So you can see that there's some correspondence in areas where you see large amounts of ice crystals and areas where you see large amounts of snow, although it's difficult to see from these plots and doing a comparison with the eye to really tell if there's correspondence or not. So now we can take the ratio between the ice crystal ice-water path and the total and obtain this fraction that can tell us more specifically what the relationship looks like. And you can see that it's not a constant ratio throughout the storm. It really depends on where you are. in these heavier precipitation convective regions, we see a relatively low ratio, which indicates that we mostly have snow within the radar volume. Whereas if we look along the edges of the rain bands, or within the moat between the main rain band and the rest of the storm, you can see that there's these high values between 0.8 and 1, where we mostly have ice crystals within the radar volume. So we can look at distributions of this ratio that I've been showing you from multiple radar scans to see how this property is distributed in the storm. And we can also separate that depending on whether we're looking at just convective elements or stratiform elements or the entire storm. And regardless of whether you just lump everything together or you separate it into convective and stratiform, these distributions really don't look all that different from each other. We generally have a peak at about a 20% fraction between the ice crystals and the total amount of ice water. And we have this then long tail that extends outward from the peak all the way out to 1. It's basically a gamma-like distribution within the storm. The one exception, though, is that if you look at this weak echo case and only look at the very light precipitation regions of the storm, 20 dBz or so, you can see that the distribution changes quite a lot, where you end up with this peak that's shifted a bit towards the right, and you end up with a much heavier tail, where some of these larger ratios are present within the storm. And this is telling you that it's really those weak reflectivity regions where the ice crystals are predominating within the storm. And that tends to be a region that could be difficult to represent numerically within the tropical cyclone. So to make this easier to compare with model simulations, there's about 40,000 observations within each of these distributions. It's not very portable to compare with a model simulation. You can actually fit a gamma distribution to these distributions and end up summarizing the ice-water path ratio using just 3 parameters within the generalized gamma distribution function. And this is something that we undertook in an attempt to make this easier to compare to model simulations in the future to reproduce these distributions. And those were the results from Arthur. I'll just quickly flip to the results from Irene in looking at these distributions and show you that, in general, the same conclusions are evident from these results as well. You'll see there's a little more of scan-to-scan variability if we look across the entire life of the storm, and that's because Irene was much more asymmetric than Arthur was. So depending on whether you're looking at an early or a late radar scan and what side of the storm you were on, there is some variation in this ice-water path ratio. But all in all, the distributions are relatively similar between the two cases, and we still see that the weak echo distributions are the ones that really stick out in terms of being different. So to summarize these results, we see that the results are microphysically consistent. They make sense of what we expect, that we increase reflectivity and fall speed as we go from ice crystals to dry and wet snow to grapple. And that there is this detection limit to keep in mind. The radar doesn't see ice particles that have a fall speed that's slower than about 1/4 of a meter per second. So we need to keep that in mind when we interpret these distributions. But nevertheless, in a mean sense, we think that the radar can identify the differences between ice crystals and dry snow within the storm, which then allows us to look at the total ice-water path and ultimately separate it into ice crystal water path and snow and grapple water path, and then take that ratio that I showed you. And the largest values of this ratio tend to be along the margins of the storm within the weak reflectivity regions. And you can certainly see that if you look at distributions, which tend to be gamma-like in their distribution and have a large tail within these weak echo regions below 20 dBz reflectivity. And so thank you very much. I'd be happy to take any questions on both parts of the presentation if you have them, and I appreciate you giving me the time to show you today these results.
Thank you, Evan. Any questions?
So radars, as we know, typically see just the biggest particles. And so I'm wondering if there's an implicit assumption that when you have snow and you really, d to the sixth is saying we're just really observing the snow. Is there an assumption that there is no ice crystal population mixed in with that, or how would that affect your ratios if there were a significant size distribution from crystals all the way up to aggregates?
Yeah, I think that's an important point, because these particle identification schemes, of course, give you the hydrometeor that makes the dominant contribution to the radar signal, and those are generally the largest particles. I think that is ameliorated somewhat by the fact that we are looking at this ratio within the vertical rather than trying to get a ratio within a horizontal cross-section. But it is a concern, and if there were a scheme that could give us a little bit better of an idea about the breakdown, not just the dominant contribution, but maybe secondary contributions as well, that would be very well fit to this purpose, I think.
If you wanted to measure that distribution of particles, what range would you need to cover?
In terms of if you wanted in situ measurements,
exactly.
For instance, well, typical ice particle size could be maybe 30 microns or smaller, all the way up to, a snowflake could be a millimeter or two across. So it is a large range to cover in terms of instrumentation. But something like a particle probe that gives you precipitation-sized particles, but also something like a cloud droplet probe as well, or a cloud ice probe, we'd probably need two different sets of instrumentation to be able to see the entire distribution, I would expect.
And if I take it, and it's important, it is important to see the entire spectrum.
Yes.
And not just one part, because then you don't know again what the other part is doing.
Exactly. I think that to really be able to evaluate how the microphysics schemes are doing across all of their ice classes, the only way is to really either remotely or in situ detect both parts of the spectrum.
Yep.
So perhaps you could get a few A-train satellite passes that could give you some other wavelengths to get you something in especially the cloud top area where all the smaller crystals generally tend to be. I mean, that's one idea that to supplement this, just besides just NEXRAD, of course, that you could have other more cloud-sensitive radar wavelengths instead of precipitation-sensitive. Just a comment, not really how to do it or how much work it is, because I know it's not a small amount. And I guess I'm waiting for the combination of this and the first half, where you actually do some evaluation of microphysics predictions in models. So do you have any preliminary results you're willing to share that show anything from WRF, HWRF, or other model that gives you some belief in the separation of hydrometeors? Because I have my own opinions on those. You can imagine from an LFO scheme perspective, you're just going to get all Grauple, and it's pointless. But I'm curious about your experience with Morrison or other.
Yeah, this type of validation is something we're starting to work on at HRD with their modeling team. And another reason to show this to you guys today is, and I know this is EOL, but Greg is in the room. We're really interested in working with modelers to do some of these comparisons. And you were right that some schemes, for instance, modified Ferrier or LFO, they really don't tell you a lot about, separation into different ice species. And there's even the idea, of course, that separating things into bins of ice species is maybe not the best idea anyway, because things exist on a continuum in the atmosphere. So really doing some of these evaluations with fancier microphysics schemes, like ones that predict the Rime fraction, might be really rewarding. And that's something I'm certainly open to working with people at NCAR with, and also at HRD as well. So no results, unfortunately.
Well, I have one suggestion when you do that and compare it to the models, I would make sure that you're comparing what the radar would see in the model distribution rather than what's actually completely in there in the model. Because, like you said, the radar is going to really be measuring the largest end of the size spectrum and not really seeing much effect from the smaller particles, whereas the total mass might be completely different. So it might be interesting. Are you staying? I have a different question. But let's
So I saw on the slide that started the whole part 2 that you have Michael Bell as a contributor, and I've just had a good couple of conversations with Michael and Bonnie Brown at Hawaii. Michael's now up the road at CSU. And Bonnie is submitting a paper probably this week that's analyzing, I don't know if it's Arthur and Irene, but it's Arthur and something from the East Coast landfalling and comparing to a variety of microphysics. Bonnie's already got one paper out on that. And then another thought I have is, what Scott said is you can, of course, do forward operators on the model output to get that, and that's something I've installed in WRF myself. But I definitely would agree with your point that the binning of different species is not the way to go here. It's an artificial binning in the ice category, in particular, but just more consideration to more complexity. In fact, because my particular version of microphysics is going to have 1/10 of the cloud ice of everybody else's, but mine's all going to be the 30 micron size cloud ice, which is why it has 1/10. But all mine's in the snow category. So, word of caution here, make sure you do apples to apples comparisons, because a lot of previous people have done a very non-apples and apples to oranges comparison because they just don't know the differences. So realize that schemes are arbitrarily creating species that need to be considered in a verification exercise. That's all.
Well, let's talk afterwards about doing something like this comparison.
So I have one more radar nerd question. So you had an S-band profiler, and I'm not a profiling expert, but how did you take into account the vertical velocity, airspeed, and separate that from the fall speed? Because sometimes you can use Bragg scatter, and if you have the time series and the spectral data at S-band, I'm guessing, but most of the time probably not. And how much would that impact the overlap between the fall speed of the different categories? I mean, there's lots of other factors there. It may be impossible to say, but
well, that's something that Sergey and I talked quite a bit about because there is really no way at S-band to use the spectrum to break it into different particles. If we could do that, that might be a great way to actually get some of these ratios independent of the dual polarization radar. So our perspective on that is that this causes the distributions to be broadened when you don't account for the vertical velocity of the air. But we expect that in a mean sense, the means are somewhat similar to what they would be if you could somehow account for that vertical velocity. So this is maybe somewhat of an unsatisfying answer, but it is a difficulty in this kind of analysis for sure.
Any other last question? If not, then let's thank Evan one last time. Thank you.
Thank you, guys.